have to find the capacitance of a parallel plate capacitor in which the space between the two plates will be filled by two dielectric media of dielectric constant K1 K2 diagonally. In the diagram, we have two parallel metallic plates, plate 1 and plate 2, and these two plates, that means plate 1 and plate 2, are separated by a distance d. So here d is the distance between the two parallel plates of the parallel plate capacitor. D is the distance between the plate 1 and plate 2 of the parallel plate capacitor, and the height of each metallic plate of the capacitor is L. L is the height. L is the height of each metallic plate of the parallel plate capacitor. So at the lowest point, the vertical distance is y equal to 0. Y will be equal to 0 at the lowest point of each plate. Here y equal to 0. And at the highest point, the vertical distance or height will be y equal to L. The point at which y equal to 0, x will be 0. No, x will be 0 at the point at which y equal to 0. Here x is equal to 0, and at the other end, that means at the point of the plate 2, x is equal to d. Now the space between the two parallel plates is filled by two dielectric media diagonally, as according to the diagram, or in this way. The space between the two metallic plates will be filled by two dielectric media diagonally, and these two dielectric media have the dielectric constants K1 and K2. We consider an elementary portion in this way, an elementary portion or a thin portion of these two dielectric media and they will be denoted or denoted by different way to differentiate the two elementary portions having dielectric constant Q1 and K2, and this angle is theta. Angle by the diagonal with the plate 2 is theta. This angle is theta. Here the horizontal length of the elementary portion of dielectric constant K1 is x, and vertical height or height of the elementary portion of the dielectric constant K1 is y. Horizontal length, and this angle will be again theta, alternate angle. And also here the elementary portion of dielectric constant K1 is denoted by yellow color, and in this case the capacitance of this elementary portion is DC1, which has dielectric constant K1, and the other elementary portion having dielectric constant K2 is denoted by blue color in this way, which has horizontal width, that is d minus x is the horizontal width of this elementary portion having dielectric constant K2. Capacitance of this elementary portion is DC2. Capacitance of this elementary portion is DC2, and the horizontal width of this elementary portion will be d minus x. D minus x. This is d minus x, horizontal width of this elementary portion. Let the space between the two plates of a parallel plate capacitor be filled with two dielectric media of dielectric constants K1 and K2 diagonally. K1 and K2 diagonally. Let also DC1 and DC2 be the capacitance of the elementary portion of dielectric constant K1 and K2 and horizontal with X and D minus X. DC1 and DC2 be the capacitances of the two elementary portions. Two elementary portions of horizontal with X and D minus X. X and D minus X. And height dy, we can denote the height dy, height of the elementary portion. This is dy in the diagram, height of the two elementary portions. Area of each plate will be A, capital A, of height dy. This elementary portions, form a series combination. These elementary portions form a series combination of capacitors of two two elementary capacitors DC1 and DC2. Two elementary capacitors DC1 and DC2. Between the two parallel plates of the parallel plate capacitor. Between the two plates of the parallel plate capacitor. Of the parallel plate capacitor. Now, the value of capacitance of these elementary portions are given by DC1 is K1 epsilon 0, dielectric constant into permittivity, K1 epsilon 0 into area of this elementary portion. Area of cross section of this elementary portion will be P dy divided by X. X is the horizontal width. In this case, cross sectional area will be B dy. B is the breadth of the elementary portion. We can denote the breadth B. B is the breadth of each plate, and that is denoted on the highest plane of the capacitor, and also we can denote on the lowest plate. B is the breadth and dy is the height. That's why area of cross section of the elementary portion is B dy. That is the elementary portion, where B is the breadth of each plate. B is the breadth of each plate. Also dc2 equal k2 epsilon 0 b dy divided by d minus x. Here for the elementary portion having dielectric constant k2 and capacitance dc2. For dc1, for the elementary portion of capacitance dc1, dc1 is the capacitance of this elementary portion, and b is the width, d is the width, and dy is the height. That's why area of cross section is b dy, and dc1 will be k1 epsilon 0 b dy divided by x. This will be the capacitance of this elementary portion. Now for the elementary portion having dielectric constant, dc2 is the capacitance of this elementary portion having dielectric constant, and in this case horizontal width is d minus x, and dy is the height, and b will be the again breadth on the cross section. In this case, capacitance of this elementary portion will be k2 epsilon 0 b dy divided by d minus x. d minus x. Again, if we draw the diagram of parallel plate capacitor, this angle will be theta, and height of each plate of parallel plate capacitor is L, and width is x, not dx. It should be x. It should be d, not dx. D, and this width of the elementary portion is x, and this height is y. Uh, that means distance of this elementary portion of capacitance dc1 from the highest plane is y. Height of the elementary portion is dy. It should be d, not dx. We can give the name of the two triangles pqr and pmn. Bigger triangle is pqr and smaller triangle is nmp. From the triangle nmp, tan theta equal x by y, perpendicular by base. Tan theta equal x by y. Again from the triangle, greater triangle pqr, from also from the triangle pqr, we can find that the value of tan theta, this width is d, and that is perpendicular of this triangle pqr is d, and base is l. Tan theta is equal to d by l, perpendicular by base, d by l. If we compare the values of tan theta, uh, two values of tan theta equal to x by y, and tan theta is equal to d by l, tan theta is equal to d by l, then we get x by y equal to d by l. Comparing the two values of tan theta, we get x by y equal d by l, or comma x equal d by l bracket closed into y, d by l bracket closed into y, that is the expression of x. Width of the elementary portion having capacitance dc1 is x, which is d by l into y. Therefore, what will be the value of dc1? What will be the value of d minus x? That is the width of the elementary portion of capacitance dc2 is d minus x, which is d minus y by l into d. D is taken common under bracket l minus y divided by l. L minus y divided by l. That is the expression of d minus x. Now we can put the expression of x and d minus x in the expression of dc1 and dc2. D minus x equal to d bracket open l minus y divided by l. So now we can find the expression of dc1 and dc2, that is the expression of capacitance of the two elementary portions. So dc1 will be equal to, it was k1 epsilon 0 b dy divided by x equal, therefore dc1 equal, putting the expression of x, we can write k1 epsilon 0 b dy divided by, putting the expression of x, which is d by l dot y, equal q1 epsilon 0 under bracket l dot b or b dot l bracket close dy divided by d dot y, d dot y, d dot y. Therefore dc1 equal to k1, dc1 equal to k1 epsilon 0 a divided by d, k1 epsilon 0 a dy divided by dy. So finally we get the expression of dc1, that is capacitance of the elementary portion having dielectric constant k1, is equal to k1 epsilon 0 a divided by d bracket closed into dy by y, where a is the area of each area of cross section of each plate. So dc1 equal k1 epsilon 0 a divided by d bracket close into dy by y. Similarly, value of capacitance of the elementary portion having dielectric constant K2 will be dc2 equal K2 epsilon 0 a, K2 epsilon 0 a, it was K2 epsilon 0 b dy divided by d minus x. Now putting the expression of d minus x, we get what? K2 epsilon 0 b dy epsilon 0 a divided by d bracket closed dy divided by l minus y. Since d minus x, the value of d minus x was d into l minus y divided by y. D minus x was d into l minus y whole divided by y. That's why we get dc2 as, k2 epsilon 0 a divided by d bracket closed into dy by l minus y. dc2 equal k2 epsilon 0 a divided by d dy divided by l minus y. So we get the expression of capacitance of the elementary portion. Now dc1 and dc2 are connected in series combination. They will be appearing to be connected in series combination. dc1 and dc2, dc2 and dc1 are connected in series combination of two capacitors. It may be assumed that these two elementary portions of capacitance dc1 and dc2 are connected in series combination. The capacitance equivalent capacitance of the series combination equivalent capacitance of the series combination of two capacitors, two elementary capacitors DC1 and DC2, DC1 and DC2 is given by DC equal DC1 into DC2, DC1 into DC2 divided by DC1 plus DC2. Now putting the expression of DC1 and DC2, we get K1 epsilon 0 A divided by D dy by y, and DC2 is K2 epsilon 0 A D divided by D dy by L minus y. DC1 is equation 1 and DC2 is the equation 2. So finally, if we put the expression of DC1 and DC2 in DC, we get K1 epsilon 0 A divided by D bracket closed divided by D bracket closed into dy by y into K2 epsilon 0 A divided by D bracket closed dy by L minus y divided by K1 epsilon 0 A divided by D bracket closed dy by y plus K2 epsilon 0 A divided by D bracket closed dy divided by L minus y equal K1 K2 under bracket epsilon 0 A divided by D whole square dy by y dot dy by L minus y whole divided by, now we can take common epsilon 0 A divided by D. In the denominator we can take common epsilon 0 A divided by D. Epsilon 0 A divided by D dy is also taken common under bracket Q1 by y plus K2 by L minus y, K2 divided by L minus y bracket closed equal Q1 K2 dy divided by y into L minus y divided by K1 by y plus K2 by L minus y. Doing LCM K1 L minus y plus K2 into y divided by y into L minus y. And the numerator we should write epsilon 0 A divided by D also. With K1 K2 we have to write epsilon 0 A divided by D also. Equal K1 K2 dy divided by K1 L minus K2 K2 minus K1 K1 L plus K2 minus K1 into y, that is the expression of equivalent capacitance DC. dc equal to k1 k2 epsilon 0 a divided by d, dy divided by k1 l plus k2 minus k1 into y. So in this line we have to write epsilon 0 a divided by d. It was missing. Now k1 k2, in the expression of dc again we have to write epsilon 0 a divided by d with k1 k2. Here we can erase this part and here we can write q1 k2 epsilon 0 a divided by d into dy divided by k1 l1 plus k2 minus k1 into y. That will be under bracket. dc, that is the capacitance, equivalent capacitance of the series combination of two elementary capacitors dc1 and dc2. Therefore c is equal to dc, y equal to 0 to y equal to l. Therefore c equal to integration dc y equal to 0 to y equal to l equal integration 0 to l. Now putting the expression of dc, k1 k2 epsilon 0 a divided by d, dy divided by k1 l1 k1 l plus k2 minus k1 into y equal. Now k1 k2 epsilon 0 a divided by d are constant. We can bring k1 k2 epsilon 0 a divided by d outside integration. Integration 0 to l dy divided by k1 l plus k2 minus k1 into y k1 k2 epsilon 0 a divided by d and after integrating we get log base c k1 l plus k2 minus k1 into y, k1 l plus k2 minus k1 into y. dy by y, we have the change form of y. That's why for integration we have to divide the result by the differentiation of the change form. That is, we have to divide this by dy of k1 l plus k2 minus k1 into y. Bracket closed, third bracket closed, 0 to l equal k1 k2 epsilon 0 a divided by d epsilon 0 a divided by d under third bracket log base c under bracket k1 l plus k2 minus k1 into y, k2 minus k1 into y divided by ddy of k1l ddy of k1l plus ddy of k2 minus k1 into y. Third bracket closed, second bracket closed, then third bracket closed, 0 to l equal k1 k2 divided by epsilon 0 a divided by d, k1 k2 epsilon 0 a divided by d log base c k1 l plus k2 minus k1 into y divided by 0 because ddy of k1l is 0 because k1l is constant K2 minus K1 can be taken outside ddy. K2 minus K1 ddy of y, bracket closed, third bracket closed, 0 to L, equal Q1 K2 divided by K2 minus K1 can be brought outside the third bracket, K2 minus K1, Q1 K2 divided by K2 minus K1, epsilon 0 A divided by D under bracket log base E under second bracket Q1L plus K2 minus K1 into Y, second bracket closed, third bracket closed, 0 to L. Now putting the upper limit and lower limit, that is putting the value of Y as L and Y equal to 0. Q1 K2 divided by K2 minus K1, epsilon 0 A divided by D, epsilon 0 A divided by D, putting the value of Y as L, that is upper limit, log base E, K1L plus K2 minus K1, K2 minus K1 into L. In place of Y, we can put L. Second bracket closed, then log base E. Putting the value of Y as 0, then we get only K1L. Second bracket closed, Q1L plus 0, second bracket closed, then third bracket closed, equal Q1 K2 divided by K2 minus Q1, epsilon 0 A divided by D, third bracket open, log base E, under bracket we can write only K2L because K1L and minus K1L will cancel out, and under bracket we can write K2L minus log base E K1L, K1L. First bracket closed, third bracket closed. K1 K2 divided by K2 minus K1, epsilon 0 A divided by D, log base E, K2 by K2L divided by K1L. Using the formula of logarithm, K2L divided by K1L, first bracket closed, in then second. Therefore, C equal to K1 K2 divided by K2 minus K1, epsilon 0 A divided by D, K1 K2 divided by K2 minus K1 bracket closed, epsilon 0 A divided by D, log base E K2 by K1 under bracket K2 by K1, bracket closed. So this is the final formula of capacitance of a parallel plate capacitor, in which the space between the two plates is filled with two dielectric media of dielectric constant K1 K2 diagonally. C equal K1 K2 divided by K2 minus K1, epsilon 0 A divided by D log base E K2 by K1. So this is the capacitance. This is the capacitance of a parallel plate capacitor, in which the space between the two plates, space between its two plates, between its two plates is filled with two dielectric media of dielectric constant K1 K2 diagonally. Two dielectric media of dielectric constant of dielectric constant Q1, K2, K1 and K2 diagonally of dielectric constant Q1, K2 diagonally.